The goal of our project was to design an experiment to measure the thermal expansion coefficient of a material using a Michelson interferometer. Here's the basic design of a Michelson interferometer, with a laser going into a beam splitter and the resulting beams reflecting back into the beam splitter, producing an interference pattern on the screen. To measure the thermal expansion, we replaced the translation stage mirror with a mirror glued to a rod, in our case an aluminum rod. By heating the rod, it will expand and we will be able to observe the collapsing of the fringes. Since we know the wavelength of the laser, we will be able to determine how much the rod increases in size for a given increase in temperature based on the number of collapsed fringes. To construct the interferometer, we started by aligning the laser source using a rail screwed into the table and an iris diaphragm on the rail. After we aligned the laser, we set the translation stage mirror in the beam path, rotated it so that the reflection passed down the throat of the laser. We did the same with the beam splitter using the reflection that came back off of it. Finally, we set the tip tilt mirror in the beam path exiting the beam splitter and used the fine adjustment knobs to set the mirror so that the reflections from both lasers overlapped. One major problem we ran into while building the interferometer was the presence of astigmatism in the interference pattern we saw on the screen, as demonstrated by the interference pattern in Figure 1. Our first instinct was to assume that the components we had used to build the interferometer were constructed and mounted perfectly and that the problem was in the alignment. With this in mind, we rebuilt the interferometer, starting again with aligning the laser and adding the components, doing everything we could to ensure the alignment was true, but found no appreciable change in the astigmatism. At this point, we realized that one of the elements was causing the astigmatism and tested both mirrors and the beam splitter using an XPZ Zygo interferometer. We found that the translation stage mirror was causing the astigmatism, but needed to check if it was the mirror itself or the mounting. By analyzing the mirror outside of the mount, we realized that the mirror mount combination was the problem because the mirror was too thin, so it was easily deformed by the mount. To fix this, we swapped the translation stage mirror with a thicker mirror, which solved the astigmatism problem.
So here's our Michelson, except we've swapped out the mirror on the translating stage with a mirror attached to an aluminum rod wrapped in a heating foil that is getting current supplied to it through a DC power supply. And as we increase voltage due to thermal expansion, the aluminum rod's going to expand and we can see the fringes collapse, and through the temperature change and the difference in collapsed fringes, we can find the coefficient of thermal expansion for the aluminum rod.
As you can see, the temperatures are going up fairly quickly, and so the fringes are collapsing fairly quickly as well. Our experiment found that the coefficient of thermal expansion for aluminum is 24.3 times 10 to the negative 6, which gives an error of 1.25%. Our experiment also found that the coefficient of thermal expansion for glass is 19.8 times 10 to the negative 6, which gives an error of 120%. The discrepancy between these errors is due in large part to the method of collecting the data. For the aluminum rod experiment, 2 students collected data, one changing the voltage on the heating foil, recording temperatures and number of fringes. The other student watched the fringes collapse for the entire experiment. For the glass rod experiment, only one student collected data, meaning every time they took note of the temperature or number of fringes, or changed the voltage on the heating foil, they had to estimate the number of fringes that collapsed while they were not looking at the interference pattern.